Welcome, Algebra 2 students, to our Section 1.2 outline from Unit 1. My name is Mrs. Lasner, and I will be the teacher going through this outline with you today. And this outline today is focused on evaluating, but in a function context. So in your previous lesson, Section 1.1, that was focused on evaluating expressions, and really focused on making sure you pay attention to that order of operations, PEMDAS. We never graduate from using the order of operations correctly. It's such a crucial process to use. So we'll be doing a lot of the same stuff you did in Section 1.1, but in a context related to functions. So we're also going to show you several representations of a function in this outline and how you would evaluate in that representation. Now, just a quick reminder what a function is. It's a relationship between two variables, two variables where there's only one output for each input. So if you think of that in terms of x and y, you're only going to get one y value for every x value. Only one output for each input. So that's what we mean when we say a function. So already it implies that there are two variables, okay? And in this particular type of a relationship known as a function, there's only going to be one output for every input. And for that reason, we can give it a special notation or a special name. And that's what this part down here is talking about. So these functions, these relationships between two variables where there's only one output for each input, are typically named with lowercase letters like F and G. I'm guessing F most likely because it's, the first letter in the word function, and then G because it comes right after F in the alphabet is why those are commonly used. So, but it doesn't have to be F or G. You can really name a function with any letter you want, and they don't have to be lowercase. It's just that that's how you will most often see them represented. So suppose a function is named F, lowercase f. Then another symbol that we could use to refer to the output of that function or the y value of that function is this notation right here. F, lowercase f, parentheses x. Now it's very important that you do not confuse these parentheses with multiplication. So in this context, the parentheses that you see there do not mean to multiply. They do not mean multiplication. So it's important that we distinguish that when we're dealing with a function context. So how do we know it's a function context? Well, you look for things like the lowercase letters, okay, typically F or G, and a lot of times you'll notice that in the parentheses will be like an X value very often. So lowercase F or G, parentheses X, or some other variable, that is most likely a function. Probably is a function, and therefore those parentheses do not mean multiplication in this context. So single letter, parentheses, single letter, you're probably dealing with a function. Okay, and then not only does this not mean multiplication, but this symbol, F parentheses X, which by the way, when you read that out loud, we say F of X. That's how you would read that out loud. The output of the function is F of X. Now, that is just another name for the output, for the y value. So y and f of x can be used interchangeably. They both stand for the output of a function, right? Because a function is dealing with two variables, something that goes in, something that comes out, and the f of x is referring to what comes out. So, let's say we wanted to know the output of a function f when the input is 4. That could be communicated in 3 different ways. We could either just say it as it is. Hey, Johnny, what's the output of a function f when the input's 4? Right? Just say it. But because y value is another name for output and x value is another name for input, we could also say it that way. Hey, what's the y value for this function if the x value is 4? But if we can get ourselves to a point where we can recognize function notation, then that's what this symbol is saying all in one little tiny package. Because this F parentheses 4 is referring to the output. It's like the name of the y value. And this little 4 on the inside is referring to the input, right? If you notice up here, that was an x value, or that was a letter x, and that letter x is often used to represent the input of a function. So that's where we put the value of the input, is inside those parentheses. So this is sort of, this f of 4 is referring to the name of the output, or the name of the y value that has an input of 4. That's paired with the x value of 4. And so it's asking us to find that, because f of 4 is the name. Now they want us to find the value of the y when the x is 4. Okay, so let's go ahead and look at a few representations of how we would do that. So in these first few examples, the function that we're given here is represented with a table of values. And in a table of values, you'll often have one column for the inputs and then another column for the outputs. So when I'm being asked to find f of 4, remember that's the name of the y value that's paired with x equals 4. So I would have to go find the x column, look in it to find where x is 4, and then whatever the matching y value was for that x value of 4, that's my f of 4. So in this case, f of 4 is equal to 51. F of 4 is the name of my answer. That was the name of the y value that's paired with 4, and then 51 is the value. So this doesn't do anything mathematically other than just give that value a name. So what is f of 4? F of 4 is 51. That's saying, what's the y value when x is 4? Oh, the y value when x is 4 is 51. Kind of gives this 51 a little bit more meaning, I guess. All right, so then let's try with a few other inputs. We want to find f of 1, same process. We go to the input column. We locate where x is 1, follow over to the output column and go up. That's 7. So f of 1, right, that's the name of our answer, has a value of 7. That's the value of our answer. Similarly for f of 2, go to our input column, locate 2, follow it over to the output column. We see that it's 12, and therefore our value for f of 2 is 12. So that's in a table context, right? And sometimes when we're working with functions, it doesn't always go input to output. Sometimes we want to find what the input was when the output was something. So we have to kind of work backwards sometimes. So if we're trying to find an input when the output is 10, for example, there's 3 different ways we could ask for that. We could either just say it out. Hey, what's the input of this function if the output was 10? And then again, since x value is referring to the input and y value is referring to the output, we could just say it that way. Hey, what was the x value that made the y value 10? Now, when we're in a function notation context, which is kind of what we're focusing on today, it would look something like this, where the value would come, this is the value of f of x, right? It comes after the equal sign. So what is x? If f of x equals 10, right? So f of x is the name of the output, right? It's the name of the output. And then 10 would be the value of the output. And what we are looking for is the x. We want to kind of go backward and find what was this guy. What did the input have to be to land on an output of 10? So we find ourselves having to sort of work backwards. Work backwards. So if we're looking at a table, that just means that instead of finding 10 in the input column, instead we would look for it over in the output column. Okay, we'd go to the ending values first and kind of work our way backwards. And then we'd see, okay, 10 was the output when 3 was the input. So then in this case, x must be 3. And why is x 3? That's because f of 3 was 10. So if f of x is 10, that x right there must be 3. So that's working backwards in table form. So in these next set of examples, the function that we're looking at here is not given to us in a table form, but more in a graph form. So this is another way to represent a function, is in the form of a graph. And when you're reading a function when it's only given to us as a graph, then we find that all of our x values or inputs are along this horizontal axis. So that's our axis of inputs or x values. And all of our outputs or y values go along the vertical axis. So that's how we read input and output when we're dealing with a graph. So I notice here that this is a function j, that they're telling us that's the name of this function. I don't know why it's j, we'll just call it just cuz. All right, function j for just cuz. And we see that it's graphed here to the right. And so we have a question here, what is the output? So that's a y value we're looking for when the input is 5, right? So we can show that notation-wise like this. What is j of 5? This is the name of the output. And we're going to go try to find the value of the output. Okay, so what I do for that is I go over to this input axis and I go, I'm going to go over to 5 because that's my input. And then I have to follow that up to the curve. Let's see, or in this case, the line, the graph. And you have to see, well, what point is on the graph when the input is 5, and then you trace that over to the output axis, which is the vertical one. Now this is interesting because the output actually matched the input, right? That doesn't always happen. In this case, it happened. So j of 5 is 5. This is the value of my answer. The name of my answer was j of 5, and that was referring to the y value when x is 5. And then this is the value of that. Oh, the y value when x is 5 is also 5. J of 5 equals 5. Okay, so then what is j of 1? Well, similar process. You have to go over to 1 on your x-axis and then follow that up to where the graph is to see, okay, that's the point on the graph where the x is 1, so what's the output there? You follow it back to the vertical axis. Oh, it looks like that output was 2. So j of 1 is the name of our answer, and then 2 is the value for our answer. This one here, what is j of negative 6? Well, this one requires me to go backwards a little bit, right? I have to go backwards on this x-axis because it's negative. So I'll go all the way to there. So I get to negative 6 on the input line, right? Whatever's in the parentheses here goes along this horizontal axis. And then from there, I trace it to the graph. Now notice the graph isn't going up here though. I have to go down right here. There's the graph. And so then I look over to the vertical axis. Well, what's the value of the output? That'll be found on the vertical axis that matches up with that point, and it's negative 1. So this is equal to negative 1. So j of negative 6 was the name of our answer, and then negative 1 is the value of our answer. Now, again, just like we did with tables, sometimes we're going to ask you to reverse that process, to work backwards. So then when we do that, it will look something like this. J of x is equal to negative 1. Notice that the value is coming after the equal sign. So they're saying this is the value of the output, and we need to find the input. So in that scenario, we are not going to start on the horizontal line. We're going to start looking on the vertical line. Okay, so I'm going to erase these. I'm going to get these things out of the way so we can kind of do that from refresh. And we're going to say, okay, this must be an output because it's coming after the equal sign. So I am going to locate that on the vertical axis because that is the axis of outputs. And then I'm going to scan right to left looking for my graph. My graph is over here. So I had to go left to find it. And then I will go up to my input line, my horizontal line, and go, oh, that's at negative 6. So x must have been negative 6 to produce a y value of negative 1. Okay, so why don't you guys try number 8? So again here in number 8, we see that the negative 2 is coming after the equal sign. So that means that the negative 2 must be an output. It must be a y value. So we would have to locate that along our vertical axis, which is right here. And again, there's no graph matching to the right of that, so we'd have to go left, which is all the way over this direction to get to the actual graph itself. And then we'd have to come up to our input line to see what the matching x value was to create that point. And I can see that the x value there was negative 9. Okay, so moving to our next set of examples. Another way that you will see functions represented is by using expressions. So here I have lowercase k of x being represented by this expression right here. And w of x being represented by this expression here. This is an absolute value expression, and this is what we call a quadratic expression because the x is being squared. And these expressions are basically like rules. They're telling you what to do with the x once you get it in order to find y. So this is a very common thing you'll see and be asked to do is find different outputs given different x values. And so this is what that looks like when we're asking you to do that. So maybe I'll just start with number 9. So it's saying find k of 4. Okay, so k of 4 is the name of our answer, and it basically means the y value from the k function when the x value is 4. That's what it's basically saying all in one little package. So our job is to try to find the value for that. So what I'm going to do is write it all out at first. K of 4 is equal to, and I will use this expression that I've been given as a rule to find values of k of x. And wherever I see an x on the inside there, I will replace this x with that in the expression. So here I see a 4 on the inside. So when I go to the expression, I'm going to replace the x that was there with a 4 and then follow the order of operations. So the order of operations, I need to do whatever's inside the function first. The 4 plus 6 will have to be done first. So then this is the absolute value of 10. And then we know that the absolute value function only changes the sign of a number if it's negative. If the number's positive, it just sort of stays the same. So the answer is 10. So that's the value of the answer, right? This k of 4 is just the name of the answer, not the value. And so you don't have to do anything with this. See, sometimes students get confused when we plug the 4 into the function notation. They think they have to do something on this side, like maybe multiply these two or divide something. But no, there's no actual math going on here. This is just a name. The name of the y value when x is 4. And then this is the value. So this is the only side you actually have to do something on, is the side where we're actually evaluating. So k of 4 is 10. Now, number 10 asks us to do something similar with the w function, and you may notice in the w function there's multiple places where there's an x in the expression. So I have to substitute whatever this value in the parentheses is. I have to substitute that in 2 different spots, wherever there's an x. So in this example, where x is 3, I'm going to have to substitute that 3 in twice, wherever the input is, okay? And when I write this out, I like to go ahead and write the name of the answer. Again, I'm not going to do anything with it. It's just the name of my answer, just to keep track of what the input is. The input is 3, and that input is going to go in wherever there's an x. So in these 2 spots, where I'm squaring the number and then multiplying it to 3, I had to replace both of those where it used to be x with a 3. And then I will go ahead and work out that order of operations. Again, on this side, I don't do anything. This is just the name of my answer. Over here, I have to follow order of operations. So I see I've got, I don't have any parentheses, but I do have exponents. So I need to do the exponent first. So that means I need to square the 3 to get 9. I can go ahead and multiply these as well. And then you see we have multiplication and division that come next, right? Remember, they just sort of are one category and you go from left to right. So I can go ahead and multiply the 2 and the 9. And then your last category, of course, is addition and subtraction from left to right. So I can add all of these numbers up. So I get 18 plus 10, basically, or 28. So this is the value of my answer, right? The name was w of 3. Again, I didn't have to do anything on this side. This is just letting me know that I am now replacing all the x's with 3. This is the value. So I could say that w of 3, the y value of w when x is 3, is 28. Now, in number 11, it's the same process, but just wanted to try, with a negative value and a decimal to kind of get that practice going. But the process will be the same. I just have to take that negative 0.5 and sub it in wherever there is an x in my expression. So I always start out by writing the name of my answer. And then I would have to replace the x with negative 0.5 and then square it. Plus 3 times negative 0.5 and then plus 1. Okay, so I'm going to follow the same order of operations as the last time. I'm going to begin with the exponent of 2. And I'm going to point this one out a little bit more because it is negative. When you square a negative, it will turn positive because you're basically multiplying that negative twice as well. So not only am I multiplying 0.5 to itself, but I'm also multiplying negative 1 to itself. And then that's what causes those to cancel out. So then I end up with a positive. So this is going to end up being 2 times 0.25 because 0.5 times 0.5 is 0.25. And then over here, when I multiply a positive by a negative, that will turn out negative. It'll become negative 1.5 and then plus 1. And then I'm moving now to multiplication and division. So I'm going to multiply these 2 times 0.25, get 0.5. And then now I can go ahead and add and subtract from left to right. So when I do 0.5 minus 1.5, that gives me negative 1. And then plus 1 gives me 0. So actually the output for this is 0. So the name for that output was W of negative 0.5, and the value for that output was 0. So why don't you guys go ahead and try number 12. Okay, so in number 12, we can see we're working with the K function. And the input we're going to use is negative 9. So we start by writing the name of our function, and that equals the absolute value of negative 9 plus 6, because basically wherever there was an x before in the original equation, I replace with negative 9. Order of operations says to do whatever is inside the function first. So in this case, I'll have to add negative 9 and 6 first and get negative 3. And then at the end, I will apply the function. So the absolute value of negative 3 is positive 3, so that's the value of my answer. Okay, now in numbers 13 and 14, this can really sometimes throw students off because now we see not only a number in our input, but also another x. So we have an x in our input, and then also an x in our expression that we're supposed to be plugging that into. And so what I want you to think of is when you see what we call a binomial. That means when you are adding two things or subtracting two things. A binomial as your input. Understand that that whole entire expression has to stay together and has to replace the old x in the expression that you are substituting it into. Let me show you what I'm trying to say here. So for number 13, here's the name of my answer, k of x plus 3. And what has to happen is I have to take this x plus 3, all of it, and it has to stay together. And it has to go in place of x in the original expression. So I've got x plus 3 plus 6. So notice that this whole entire binomial just took the place of this x in the original expression. So you kind of are taking one x out and replacing it with a new expression, because that's what this is telling us to do. This name, k of x plus 3, is saying what is the output of k if I plug in x plus 3 for x, if my whole input is x plus 3. So that's what has to happen. No, I don't multiply this to the old x. I just take that old x out completely and replace it with x plus 3. And you don't need parentheses here. I just put them there for emphasis to show that this input has to stay together. But it's not really needed in terms of order of operations. That was just there to help you see that these have to stay grouped together. So then that tells me to just go ahead and add the 3 with the 6, because I can't add the 3 with the x, right? X is a variable. So then that gives me x plus 9 inside my absolute value, and that's as far as I can go. That's actually the value of my answer. Okay? So that means k of x plus 3 has a value of, absolute value of x plus 9. So when your input has an x in it, then your final answer will most likely still have an x in it, because it's just kind of giving you a new expression, really, is what just happened there. Okay, so let's go ahead and do number 14 as well. So you can see I have another binomial, x minus 2, and now the name of this function is w, so this is going to go into this function here. So I like to start by writing out the name, help me keep track of everything, and I'm just going to highlight it here just for emphasis, right, to make sure we don't get lost. So I have 2 times this entire binomial squared plus 3 times that entire binomial plus 1. So basically what's happening there is I'm replacing the x in the expression. So this x in the expression is just a placeholder. It's just the place where we're going to put whatever input we're given. And the inside of these parentheses in function notation is telling you what that input is. So I take this binomial of x plus 2 and I put it in place of where x was in the original expression. This old x goes out, x minus 2 goes in, and I need to do to the x minus 2 in this expression what was being done to the x in the original expression. That means I'm going to have to square it right here. And as a reminder, when you're squaring a binomial, it's not just distributing the square. In fact, that will give you an incomplete answer. What we're going to have to do there is write it out twice and FOIL it. I'll get to that in a second. Here, because I'm multiplying a single term to a binomial, I'm going to have to go ahead and distribute. So that'll give me 3x minus 6. Okay, now here, I'm going to want to do the exponent first before I multiply, right? Following PEMDAS. I'm going to want to square that and then afterwards distribute the 2. So I'm going to keep the 2 there so I don't forget about it, but I'm going to go ahead and FOIL these first. So that means first terms get multiplied together, that's x squared. Outer terms go next, so x times negative 2 is negative 2x. Inner terms go next, so that's another negative 2x. And then last, negative 2 times negative 2 gives me a positive 4. So that's what you get when you square x minus 2. You end up with 4 terms from FOILing. Okay, then meanwhile, I can combine some like terms over here. I can add this negative 6 with the positive 1 and get negative 5. Okay, I can also combine some like terms within the parentheses there. So I get x squared minus 4x plus 4 is all in those parentheses, plus 3x minus 5. Then, now that I have taken care of the exponent, I can go ahead and multiply. And multiplication here will require some distributing because I have a single term being multiplied to what we call a trinomial, something with 3 terms. So I will distribute that 2 to all terms, and I get 2x squared minus 8x plus 8. I still have the plus 3x minus 5. And then the last thing I'm going to do there is combine like terms. So I notice I have like terms of negative 8x and positive 3x. I also have like terms of plus 8 and minus 5. So my final answer with everything simplified is going to be 2x squared minus 5x plus 3. That is the value of my answer. The name for my answer was w of x minus 2, and that is equal to or has a value of 2x squared minus 5x plus 3. Again, because my input had an x in it, my final answer also had x's in it. It wasn't a number, it was just a new expression. Now for the last part of this outline, we're going to be looking at when you're given an equation for a function. So this is kind of like a fourth version of being given an expression. So these were when you're given one single expression to represent all the outputs of a function. And this here is when you're given different expressions to represent the different ways we get the outputs for this one function. And the name of this type of function is called a piecewise function. Now, one thing I just want to say here to maybe ease your mind a little bit is we are not expecting you to know everything about piecewise functions after this one lesson. This concept of a piecewise function is something we are going to develop all semester long. Our only focus of it in this particular section, 1.2, is evaluation. All we want you to be able to do with piecewise functions after this lesson is be able to evaluate them. Okay? You don't have to understand everything about what's going on here. We just kind of want to expose you to what they look like and show you how to evaluate them. And then at different lessons, different times in the semester, we're going to talk more about what we mean by domain restrictions and what this might look like on a graph. We will more thoroughly develop this concept all semester long. Okay, so today, just focus on evaluating. But as a brief introduction, what's happening here is that we're given different expressions for different inputs. So these guys over here are saying, okay, when the input is less than -3, we're going to find the output using this expression. But when the input is between -3 and 1, we're actually going to switch and use this expression to find the output. And then when the input is greater than 1, the output will just always be 10. That's kind of what these are saying. And all of these are finding outputs for f of x. So the name of this function is f of x. And these are kind of like the different rules for finding the outputs. And then these are your different input rules right there. So these are like input rules. And these are output rules, or rules for outputs. Okay? So again, we're just focusing on evaluating. That's it. So here, what would it look like if we were asking you to evaluate? It would have this function notation, right? Lowercase f, which is the name of this function, parentheses, not meaning multiplication, right? This is in a function context. This -5 is representing the input. And this question is just wanting me to find the output, right? Because f of -5 is the name for that output. So when you're given given a function being represented in multiple pieces, then what you have to do is take that input and go to your input rules and figure out which one it belongs to. So -5 is less than -3 because it's more negative, right? So it would fall under this category. This input follows this rule. It's less than -3. Therefore, I'm going to use this output rule to find f of -5. So f of -5 is going to equal what I get when I plug -5 into this expression, which is -x. So there's two negatives there. One of them was part of the input, and then the other one was part of the output, right? And so they end up canceling out, and I end up getting +5. So f of -5, that's the name of my answer, has a value of +5. Similarly, for f of 1, I have to figure out which one of these rules that follows. And so I look at the different categories and I notice that this one here has an equal sign under the less than sign. This one does not have an equal sign under the greater than, which means 1 is actually not part of this rule. This is only for inputs that are actually bigger than 1. And 1 is not bigger than itself. Here, it's any input less than or equal to 1. So that means 1 is included in this input rule, and therefore I will use this expression to evaluate it. So to find f of 1, I just plug in my input of 1 into that middle expression. Not all three, just the middle expression, because that's the one that is allowed for an input of 1. And then I just evaluate from there. 3 + 9 is 12. So that would be my answer for number 16. Why don't you guys try number 17? So in number 17, we're given an input of -3. So I have to go and find where that input would belong. And I can see that it also belongs to that middle category because of the equal sign right there under the less than sign. That means I'm including -3 as an input. And therefore, to find the output, I would use this middle expression. So I would plug in -3 into the expression and evaluate. 3 times -3 would be -9, and then add those together, I get 0. So now in 18, I'm being asked to find f of 3. So I follow the same process of looking for where the input of f of 3 is allowed. So I go to my input rules and I notice that it would match the last one because it's greater than 1. So if x is 3, right, because that's what this is saying, x is 3, and then that's greater than 1, it would follow the rule of x being greater than 1. So then the output for that is 10. And sometimes this really throws students off because they don't know where to plug in 3, right? I'm supposed to plug 3 somewhere where there's no x. So it's actually easier. If there's no x, that means x doesn't have any effect on the output. That just means that whatever x is, the output will be 10 as long as x is greater than 1. So actually you're done at the very beginning. Because remember, you don't need to do anything with this part. That's just the name of the answer. The value of the answer is 10, and we're done. So why don't you guys finish this off by trying numbers 19 and 20. Okay, so in 19, we're given an input of 0. So I have to go up to these input rules and figure out which one it would belong to. So an input of 0 would fit in between -3 and 1, right? That's an input between 0 as a number between -3 and 1. So then I would use the middle expression to evaluate it. And I would just plug in 0 for x. And I get 0 plus 9, which is 9. So that's my answer for number 19. For number 20, same thing. I have to figure out where would an input of -1/3 be allowed. Well, -1/3 actually also falls in this middle category. It's a number that's between -3 and 1. So I would use that middle expression again. And I would just substitute that in where the x is. And then you can think of the 3 right here as 3 over 1 and multiply straight across. So that's -3/3. And then 3 divided by 3 is just 1. So that's -1 plus 9, which equals 8. So f of -1/3 has an output of 8. And that concludes this video. Thank you so much for sticking all the way through. A lot of information there. So please feel free to reach out with questions, and I'll see you soon.